So good afternoon to everybody and welcome to the second Eurostruct live talk, which is this time organized rather early compared to the last one. It's only a week between these two talks. Generally speaking, we were looking into having a talk each month, but these two came together somehow. As for my person, my name is RWTH Aachen. I am a professor at the Faculty of Civil Engineering, University of Belgrade, Serbia, which is the hat I have today. And I'm at the same time president of Infrastructure Management Consultant, a company based in Zurich, Switzerland, which is essentially also quite busy with the structural assessment. My co-chair or co-moderator today is going to be Alfred Strauss. Alfred, would you like to present yourself, please?
Yes, also welcome to LiveTalk and good afternoon. So my name is Alfred Strauss. I'm also professor in structural mechanics at the University of Natural Resources and Life Sciences in Vienna. And my research interests are in bridge engineering, structural design and health monitoring, as well as safety assessment of existing structures. And I'm pleased to assist Professor RWTH Aachen and Mr. Ernst Niederleithinger, Dr. Ernst Niederleithinger as a co-moderator.
Thank you very much, Alfred. There are a couple of rules I would like you to follow. One is, if you please turn your microphone off, you are also supposed to turn your camera off, because that's then the bandwidth is going to be sufficient, I hope. The questions, if you have, you should put in a chat, and these questions are going to be answered in the Q&A session after the talk, and they are going to be handled alternatively by Alfred Strauss and myself. I would like at this place also to acknowledge Minho and which for the support, and FIB as well the boutique. This is a company that's responsible for the fleets, and they were kind enough to publish these fleets free of charge. The live talk would be recorded and will be made available on the YouTube channel. So if some of you have missed today's talk, they can anytime look at the YouTube channel. Now, I have a great pleasure and an honor to present you our speaker today. Our speaker today is adjunct professor Dr. Ernst Niederleithinger. He is the head of division 8.2 non-destructive method for civil engineering, and he is with the Federal Institute for Material Research and Testing, commonly known as BAM. Ernst Niederleithinger got his diploma in geophysics from TU Berlin and his PhD from University of Potsdam, and his habilitation is from the Rheinisch-Westfälische Technische Hochschule Aachen. After 11 years in engineering, he joined BAM, the German Federal Research Institute for Material Testing, in 2001, and currently he serves as head of the division 8.2 NDT method for civil engineering. His main research interest is in transferring geophysical tools from seismic managing and monitoring to non-destructive testing, with application in assessment of existing building and infrastructure, including their foundation, quality assurance, and so on. Also nuclear waste storage. He is a member of German Society for Non-Destructive Testing. He is also a member of German Society of Geophysical Society, then Society for Exploration Geophysicists, and European Association of Geophysicists and Engineers, as well as member, and we are proud of that, of this association, Eurostruct, and finally, not but least, but not last, but not least, and the American Society for Testing and Materials. And he serves in various scientific and standardization committees. He teaches engineering geophysics at Aachen University. The title of his talk is NDT-CE, Civil Engineering for Simple Detectors to Deep Insight and Quantitative Structural Assessment. And he is going to discuss in his talk about better tools, deeper and more detailed insight into concrete construction, about better methods, quantitative use in probabilistic structural assessment, about better rules towards standardization, qualification, and certification, and better application, digitalization, and elimination of boundaries between NDT, SHM, structural health monitoring, and BIM. And if you don't have enough of all these things, which I hope is sufficient anyway, you are going to learn something about how cosmic rays might become a game changer in NDT and civil engineering. So, Ernst, the floor is yours.
Thank you very much to everybody at Eurostruct for the invitation, and to Professor Heidin and Professor Strauss for the introduction. So the first bad news is, if you want to know something about cosmic rays, you have to wait until the end of my talk. So that's kind of the way of keeping you online for a while. So of course, all the work I will present is not entirely my work. So there are many contributions from many co-authors of my group at BAM, and also from a couple of external co-authors, too many to do this here. So the parts of the content have already just been named. So I will a little bit talk about better tools in NDT, better methods, how to apply NDT, better rules. I will keep this to a minimum, and there will be a couple of applications on the way through these topics. In the end, I will also talk about the role of NDT in civil engineering in relation to SHM, to BIM, so forming something which can be called NDT-CE 4.0. So I would start with my institution. So probably some of you have come across BAM, which is the German Federal Institute for Materials Research and Testing. We are part of the German government. We are part of the Ministry for Economy and Energy. So, and our predecessors have been founded in 1871. So this year we are celebrating our 150th birthday, which is indicated here on the bottom of my background. So we are about 1,800 employees with a mission on safety and technology and chemistry. And there's a large variety of topics, too many to be talked about here right now. But more important for today, there are departments of non-destructive testing and civil engineering, and my division, which is on non-destructive testing and civil engineering, is somehow in between both. So what we are actually doing in this division, so we are, of course, our major work is in research. So we are developing or optimizing non-destructive testing methods for concrete and other building materials. We are working on validation of new methods, on providing references, reference data, reference specimen, other kind of things. We are also working, of course, on standardization in various committees, national ones and international ones. So we are doing actual testing on site if it's a more complex task, or if special equipment is required, and are providing data analysis. And we are also providing workshops and trainings in various ways. So our main methods are ultrasound and radar. I will today mainly focus on ultrasound. There will be some hints to the other methods as well, but ultrasound will be the focus. We are also working on sensors, which can be embedded in concrete. I will show you some examples later. And we are working on something called laser-induced breakdown spectroscopy. That's a method which can be used to detect elements on the concrete surface that have very high resolution and very high speed. But unfortunately, today the time is too short to talk about that one. We are, of course, also using some standard methods you probably have heard of or are familiar with, like cover meters or the impact echo methods or the rebound hammer, but we are not doing research on that. That's not all what's done at BAM. So there are a couple of other divisions who are also contributing to non-destructive testing or monitoring in civil engineering. For example, there are divisions who are developing fiber optical sensors, who are working with infrared thermography, radiography, computed tomography, potential mapping, and optical methods. And of course, if it's needed, we are joining forces. So our application areas are in general any kind of quality assurance in civil engineering, condition assessment, and structural health monitoring. Our main application area is road infrastructure, but up to a certain extent also railway or waterways. We are covering everything between buildings, basement, foundations, roads, name it, we are doing it. We are also working more and more extensively on nuclear structures, mainly nuclear waste storage. Nuclear power plants is not a big topic for Germany anymore. And from time to time, we are also working on cultural heritage. So what is it all about? So why are we doing NDT in civil engineering? So of course, that's to keep the iconic and also the non-iconic buildings of the civil infrastructure as long as we can. There are a couple of excellent examples of buildings standing upright for 1,800 years, like the Pantheon in Rome. So the ultimate goal would be to keep the modern buildings as long as that. Probably we will not be so successful as that, but 100 years is still a very challenging goal. So what's special about the infrastructure in Germany? So probably you have seen similar graphs before. So there's almost no infrastructure left, so mainly concrete bridges here before 1945 for obvious reasons. That was the end of World War II. There was a large amount of rebuilding in the 1960s and 70s and until the 80s, and we started to have a small decline, and then we had another smaller peak after the German reunion. So, but already some of these buildings now 30, 25, 20 years old, they show some signs of deterioration. So, but our main target is still the bridges from the 1960s, 1970s, which are meanwhile, at least some of them, close to the end of their service life for several reasons. So fortunately, the state of the art in non-destructive testing has developed a lot. Probably some of you have worked with, let's say, conventional, simpler methods such as the rebound hammer or ultrasonic pulse velocity. So that's around for 50 or more years, and that's standardized and commonly used. But after the 1990s, there was a very fast and extensive development of other methods, such as ultrasonic echo, such as radar, and some other methods, which gave a deeper insight into concrete structures. In the 1990s, it was mainly still quite bulky, complicated devices, which have been slow and hard to deploy and just to be used by specialized experts. But beginning from, let's say, 2005, 2010, more and more methods came around which are easier to use, which are commercially available, and already give on-site information of what's inside a concrete structure. So one example would be ultrasonic echo testing by point contract transducer arrays, which give a direct image of the interior contract here on the small screen. This is not the end of the story, so the development goes on and on. So two examples for very innovative and very modern tools would be, for example, GPR equipment, such as the one produced by the Swiss company ProSec. Very small, very easy to use, directly attached to cloud's data storage, directly giving information on site, even using augmented reality to provide information to the user, for example, where it's safe to drill or where to check reinforcement and these kind of things. And also the ultrasonic development goes on. So on the right side, you have an example from the Russian-German company ACS, who now provides, starting from this year, a true 3D ultrasonic device called Mira 3D, which gives, with one single measurement, a 3D picture of the structures inside the concrete. So that's most probably not the end of the story. So that's just one point in time, and the development will go on. So, but the main thing is for practical application that these methods are meanwhile more or less successfully implemented in practice. So ultrasonic transmission, for example, is used to check the quality of the concrete, either in the lab, but also on site. And ultrasonic echo is used, for example, to detect tendon ducts, as in the example on the right. So, and then directly on site, we can give information to the responsible engineers what was going on. Still, there are a couple of things where we have to work on. For example, the depth of penetration for most methods is limited. 1 meter is a good guess for this limit. If we have very complex structures, the imaging methods might not be sufficient at the moment, and mapping complex or diffuse deterioration is a big challenge. And also detecting slow and small damages is a challenge. And I will provide some ideas for the solution on these techniques. But before doing it, I will show you an example how these days results acquired with commercially available instrumentation can be used in a better way than just to provide colorful images to detect rebar and to avoid hitting the rebar when drilling, or to avoid hitting a tendon duct when drilling, and these kind of things. So one challenge in Germany currently is that we have to reassess about 2,000 bridges under federal administrations because they are in, let's say, intermediate to bad condition or have structural deficiencies or other issues. So what's normally done still today with these kind of NDT is to show pictures like this, maps of the interior of the concrete with some signatures of, for example, of tendon ducts or of the thickness of the structure. So what we propose to do is to evaluate these data in a more thorough way, to check for all these influences which give indications on the potential errors and standard deviations and other issues, to provide really statistically proven quantitative measure, for example, for the depth of a tendon duct, which then can be used in quantitative probabilistic assessment of a structure. So one example is a pre-stressed concrete bridge in Bavaria, near Munich, where a very detailed assessment was done because it was known that the load capacity, according to the older standards, was not sufficient to cope with the traffic anymore. So it's a box girder bridge over a medium-sized river, 3 spans between 40 and 55 meters. So what was done first is to check what kind of parameters are really important for the probabilistic assessment. So where can we gain most of information and value out of any kind of measured values? After a very detailed analysis of the bridge, it was turned out that the position of the shear reinforcement was very important, and also the position of the tendon ducts. If we could provide very precise values on these positions, we could potentially improve the trust in the load capacity assessment and even get higher reliability values. So what was done there is to use radar and ultrasound to locate shear reinforcement in tendon ducts and to do a quantitative analysis on that one. So that's an example. So that's the cross section. We were looking for the outer tendon ducts. So we were able to see the first row and also the second row, not the inner ones, but the outer ones were the most important. And we used ultrasound and then radar to detect the precise position and depth. So we didn't just provide the colorful pictures, we also picked the positions of these tendon ducts, calculated all potential influences, potential errors, standard deviations, and so on, and put this information into structural models with all the uncertainty information. Good thing is that after this detailed evaluation, so we helped to raise the reliability index from a certain value here, 3.8, to values around 4.8. So by more than 20%, about 25% higher reliability of the structural reassessment. So that's just the beginning of the story. There's still work to be done. There are 2 recent publications, unfortunately only in German so far, but that's one path we will continue to provide a way to use non-deterministic testing methods really in the quantitative way. But there are other issues with NDT in civil engineering. I mentioned that we have a depth limit, so of about 1 meter. So, but there are lots of constructions which are thicker than 1 meter. Certain bridges, dams, also certain buildings in nuclear facilities, and probably you have other examples. What we have been done to build a really large ultrasonic instrument, which is called the LAUS, Large Aperture Ultrasonic System, So with many probes, which can be freely positioned on a surface, they are using vacuum to stick on the concrete surface. So all these red things you are seeing here are vacuum hoses. And this instrument is able to look much deeper than the commercial ones. One application example is a bridge close to my hometown Berlin, about 2 meters thick. And during the concreting, there was a heavy rainstorm. So at some point in time, the formwork was half full of concrete and half full of water. So of course, this had an effect on the concrete quality. And some of the damages were visible from the outside, but of course, the authorities wanted to be sure that there are no serious damages on the inside. So, of course, from the bottom of the bridge, it was easy to check the damages. But as this bridge was about 2 meters thick, so the commercial instrumentation failed to map the entire structure. So we used this LAU system from the top to check the position of the tendon ducts and to see whether we see some indications of any kind of disturbances above the tendon ducts. So that's one example for a vertical cut through our 3D data volumes. And you see here there are reflections, clear indications of the top of the tendon ducts, a little bit weaker on the outside because there we have less coverage by ultrasonic energy. We also see the backside, the lower side of the bridge, so with some gaps because the tendon ducts are producing a shadow. So but this looked quite good. And so we could deduct that most probably there's no big issues above these tendon ducts because otherwise we wouldn't have seen these clear echoes. Unfortunately, in some places the data look different. If we look at now at horizontal slices at the level of the tendon ducts, at some places the tendon ducts were quite clear to see, very clear echoes, very sharp at the position which was expected. But there were other places where these echoes were very blurred or even missing at some places. So we did the most simple thing to do. We asked the contractor to drill and to check whether there were some issues. And actually there were issues, there were honeycombings and so other ways of backed concrete. So, but fortunately, this could have been repaired by injection. So they didn't have to replace the bridge. So, as you've seen, the images were not perfect. We just see reflections with gaps and indications of the top of the tendon ducts. We will not be able to see the precise structures or even the diameter of the tendon ducts. That's one thing we are still working on, using input from geophysics. For example, using an imaging method, which is called reverse time migration. I will not go into the details here. So we had PhD students working on that or still working on that. And for example, for simple examples on materials like polyamide, of course, that's easier than concrete because it's homogeneous and there are holes inside. We could provide images which can be used to measure the diameter of these holes quantitatively. So if you have an unknown type of tendon duct in your bridge, this method can, for example, potentially be used to check for the type of tendon duct, so shape and diameter. Unfortunately, it's still the method under research. It's also computationally very expensive, but for some tasks it might be used. One example where we combined both the deep penetration and better imaging is a nuclear facility in northern Germany. It's a nuclear waste storage site, which has to be closed down. It's a former salt mine, and to close the former mining tunnels, a special type of concrete is used. So there's a kind of big plugs, 4 meters by 4 meters by 25 meters long. Of course, no ultrasonic instrument is able to map 25 meters of concrete. We did some trials with our LAU system and were able to locate at least some reflections from up to 7 meters. So there was no built-in structure at 7 meters. So we thought it might be a crack, and it was later proven by drill holes that there were cracks. Of course, that's a bad thing for an engineered barrier and a nuclear repository to have cracks. Fortunately, this is just a trial site, so no harm done. Our data can now be used to improve the concrete mixture and then the way of building it to provide better sealing. As we were not fully satisfied with the image quality, so this is a cross-section. I'll skip this. So we tried to use better imaging methods. So these reverse time migration I've shown before. First, we did some simulations to check whether we could image the shape of any kind of crack correctly and also detect features at deeper depths. And we saw that the conventional imaging, okay, we are seeing some things, but they are not complete. We also don't see these side boundaries and other kind of things. And using these new methods, we might become better, having the better image of this sinusoidal crack type. We also see more information of this plate, and then also we are starting to see the lateral boundaries. So we checked this using data from the actual site. And so if you look at this data, this is the conventional imaging and this is the new imaging. There are some subtle but important differences. For example, here first we thought we had two separate cracks, but using the new imaging methods, we were able to prove this is just an artifact due to a 3D shape. So actually we have one crack here at this close to 7 meters depth. And also we were able to get a better image of the plate down here below without artifacts at places where the actually there's no plate. Okay, that's work and research which has to be continued in the coming years. One other development in non-destructive testing is that we are starting to lose or to loosening the boundaries between non-destructive testing and structural health monitoring. We are using similar sensors and similar methods, and we are putting the information together to get better models and better information for the structural engineers. So our research work on embedded sensors and concrete is multifold. We are working, for example, on RFID sensors, wireless, batteryless, inside the concrete, which is able to measure temperature, humidity, or indications for corrosion or chloride content. We're using ultrasonic transducers to map stress and degradation. I will give a little bit more information on that in the next slides. And we're also doing using fiber optics. So one example for this kind of work, so you could imagine that a volcano and a bridge is totally different, but there are some things in common because they both have slowly developing damages, but at a certain point of time, the damage development might speed up and there might be a sudden collapse or eruption. And of course, we need to measure these tiny precursors of deterioration and or any kind of collapse or eruption before anything serious happens. So for volcanoes, this is done by seismologists by measuring the speed of seismic waves. And they are able to detect very small changes in velocity. So this is less than 1% change. And what we can see here that a couple of days before the actual eruption, we have a drop in velocity. And this drop of velocity occurs much earlier than any other kind of indication. So these other curves are for conventional measuring tools like inclination of the surface or changing distance between two landmarks and so on. So measuring the speed of seismic or ultrasonic waves might be a useful thing also for civil engineering. So we are doing this by doing continuously ultrasonic measurements and comparing the acquired signals. And normally, even if you put a load on a concrete structure, the signals will be almost the same. They're only very subtle changes. If you're looking at the beginning of the signals, they are very similar. If you're looking at the later part, the so-called coda, we are seeing some phase change. So it's kind of a delay of the second signal, and this can be evaluated. There's another good point for looking at this late part of the signals. We can cover a very large area, so we need not that many sensors to cover a certain part of construction. Of course, resolution is limited, but still we might be able to capture the part of the bridge where change is happening or damage is happening. some experiments done at RWTH together with the German Road Research Institutes with a network of these ultrasonic sensors in a two-span bridge girder in a full-scale load experiment. And doing this, we were allowed to put sensors in a part of this girder, and at a certain load point, we were able to provide a map of velocity change. Velocity decrease always on the opposite side of these loading points. That's because we have tension there. Some small cracks are opening, micro cracks, which are not visible. Speed goes down, and that's what we can see here. So we have an early indication of the places where tension happens. We can even, if you do calibration by using some local strain gauges, and here comparing velocity change to strain, we can calibrate these images and provide maps for strain change. That might also be a very useful tool in the future. So if you're going to higher loads, when cracks are starting to be visible, these are the red lines here, these are the visible cracks on the surface, we see that these areas of high strain are reflected by the crack pattern. It's almost the same area, except this area where the surface was covered by some sheets of paper where the cracks were simply not visible. We also see some anomalies here in our ultrasonic, let's say, strain maps, where we didn't expect any cracks, but actually there were some, because concrete is not completely homogeneous. We have some inhomogeneities here, which are also reflected in these maps. So in this, then, because we are able to map these inhomogeneities, we might even add some more information to simulations which are predicting the crack pattern. So the pattern is similar, but it's not the same. So we might be even a bit closer to the reality than the simulation. This is now, at the moment, tested in practice at the bridge over the River Danube in Ulm in southern Germany, where this bridge from the 1950s is equipped with several monitoring systems, so we have something to compare with, for example, acoustic emissions, strain gauges, and other devices. We have put our sensors in there. We are measuring the velocity changes over time, so these are data from 1 week, and of course we see mainly the temperature change, but this is now continued, and probably end of the year we will have a good example how this kind of method can be used in practice. We will do some load tests there to prove that our method really is able to detect any kind of additional damage. So finally, we have to put all these data somewhere. So that's one thing I want to emphasize. So far, the NDT world has always been a little bit separate from other parts of civil engineering. There were specialists giving reports on paper or as a PDF to the engineers, but there was not really quantitative data exchange. So the main way of exchanging data in the future in civil engineering is, of course, building information modeling. Probably we can agree of that. There are, of course, limitations to that, but still, most probably, this will play a central role in any kind of civil engineering projects. And NDT and structural health monitoring can, of course, provide information to several phases in a lifetime or in the BIM information modeling cycle. Of course, it can help to document as-built building. We can do quality assurance during fabrication and construction. We can assist in operation and maintenance, for example, to check for a couple of parameters, as well as in destruction and renovation. So, but unfortunately, there is so far no interface between BIM software and NDT and sensor data. There are a couple of projects, national and international, who are starting to work on this, to use BIM and NDT and sensor data to get to better models or even provide digital twins. But that's not standardized yet. And that's one thing we have to do. So, and the probably focal point in here will be something which is called industry foundation classes, which provide formats to exchange information between BIM and many other things, as, for example, structural analysis, energy analysis, facility management, and potentially also in the future, NDT and sensor data. So, but there is still a lot of work to be done. That's a challenge for the future. We probably can learn a lot of things from things called Industry 4.0 and the Industrial Internet of Things. So in today's smart production, so these kind of things are already used. So monitoring and NDE, sensors and devices, they all have internet capable interfaces, and they can directly talk to each other. They can provide data for scheduling maintenance, but they can also be directly connected, for example, to the economic part of the software in production. So probably in civil engineering, we still will have some kind of different systems, because I don't expect that the raw data from structural health monitoring or NDT will directly go into any kind of BIM software. So probably just the information about the results or the places where measurements have been done. This will be given to the BIM software and also visualized there. But the raw data, including all the metadata, will probably be in a separate place, because it's simply too much data probably for the BIM software. But we have to provide the interfaces here. And that's things which are still under development. Even providing this system down here, which defines formats between the sensors and devices and the databases and the persons doing the interpretation, has to be developed yet. So one project which has just started is working in that direction. It's called CASPAR. It's joint work of BAM and the University of the German Army in Munich and several industry partners, to provide something like a database system which is able to collect all kinds of data, put them in a really trusted data storage, so using blockchain technology, and providing interfaces to BIM, to CAD software, but also to any kind of analytical software. So finally, I was talking about that for this kind of data exchange, we are needing standards, but that's not the only part of NDT and civil engineering where we need more standards. In other fields of NDTs, we already have dozens of standards on certain methods, on certain sensors, on certain evaluation technologies, formats. They almost have everything done at the moment. But in non-destructive testing in civil engineering, for example, in Germany, we just have the rebound hammer and ultrasonic pulse velocity standardized. There are a couple of initiatives which are probably going to change this. I'm naming one of that. So, for example, the ECE project, I Am Safe, Professor Heidi and Professor Strauss are both in part of that, are preparing a way towards European standardization and monitoring. And that's a very important initiative, and it's very urgently needed. But also for the qualification of personnel and of institutions, we need more work to be done. So in traditional NDT, there's already very sophisticated 3-level qualification schemes. Certification is regulated and everything works in an organized way. So, so if someone has done one of these trainings, he can really be trusted to do a good job on site. But in non-destructive testing and civil engineering, we have only very simple qualifications. For example, the German bridge inspectors, they get half a day introduction to NDT. There are a couple of other courses you can take, but this is just for a limited amount of applications and also very short courses at the moment. So this is going to change. So a working group of the German Society for Non-Destructive Testing has just submitted a draft for a new qualification system. It will be just 2-level, not 3-level, but it's starting to provide a way to provide such a qualification system, which then can be trusted by customers. And I think trust of the customers, trust of the authorities is very important to expand the application of SHM and NDT. So instead of giving a conclusion of my talk, I promised to have one more thing. So one thing which was new to me a year ago and I want to share what we have done so far in that direction. So cosmic rays, one special type of cosmic ray. So I'm talking about cosmic muons. These are some particles, actually they are not cosmic rays but they are generated by cosmic rays. Some very fancy particles which are generated in the upper atmosphere, going downwards and penetrating deep into the Earth. So that's natural radiation. There's almost no harm done by them, and especially there's no additional harm done by them. There have been a lot of experiments in using them, for example, to locate voids in the pyramids. So my colleague, Professor Christian Grosse from Technical University of Munich, he is currently using GPR to check whether these results are actually true. But there are also starting to be commercial applications, for example, for checking containers for contraband, or checking radioactive waste containers for anything which is in there but shouldn't be. So, and there's a company in the UK who starts to work on commercial instrumentation, and we did a joint experiment with them. So this company is called Linkers and situated in Glasgow in Scotland. So this is the detecting system. There's not much to see from the outside. So there are detectors on top to check the incoming muons, and there are detectors down here who are checking the outcoming muons. And some of these muons are scattered when going through whatever is in between these detectors. For example, one of our BAM reference specimen made to check NDT methods. So inside this concrete specimen, we have a tendon duct, we have some reinforcement, and also a styrofoam plate. So what we wanted to see is this method maybe capable to do at the end an X-ray of a bridge without having to use X-rays and having to use radiation protection? So that's what we wanted to check. So that's why we brought one of these specimens, 700 kilos, to Scotland and put it in that detector. So we also, of course, did other measurements like GPR, like ultrasound, and actual X-ray. So we have a big X-ray machine at BAM, so we had something to compare with. Some results. This is the upper reinforcement, so we are going in layers through the specimen now. And this is the muon imaging results. And what are we seeing? We are able to see the actual reinforcement at the right place and with a quite high resolution. There's a lot of noise still. The detector is not optimized to do this. Also, this is the first ever experiment in that direction. So, but still, the result is pretty good. Of course, we can also do it by GPR, but we can't, for example, measure the diameter of rebars with GPR or ultrasound. Of course, we can do it with X-ray, but that's also very expensive, and we have the issues with radiation protection. So we also see some shadows from the other features inside because the resolution, especially in the vertical direction, is not optimal at the moment. If you look at another slice, a little bit deeper, where we are expecting to see the lower reinforcement and the styrofoam plate, we actually see what's there. You see the precise boundaries of the styrofoam plate, and we also see the lower reinforcement. We also see the tendon duct in here, which is in between the both reinforcement plates. And we see that still we see this also with the other method, but still for a first ever experiment, these are pretty good results. And that's one way we want to work on further. The main challenge is here to provide detectors which are mobile and can be brought to a bridge. That's still under development. So that's my final slide. I've talked about a lot of issues, about some new tools to do NDT measurements, about ways to use the results in practice, also things we still have to do, like the integration into BIM and some other issues. And I hope I also gave some ideas about some points to work on in the near future. Thank you very much for listening, and I'm waiting for your questions.
Thank you very much, Ernst. This was an amazing lecture. I think there is a lot of things that can be discussed with regard to your lecture. And we indeed have some questions. So I'll start myself with the first one that was actually already been posed for quite some time at the very beginning of your lecture, and this one is relating to magnetic flux and what they would like to know your opinion. What's your opinion on using magnetic flux leakage method to inspect tendon ducts?
So yeah, magnetic flux leakage is mainly used to detect wire breaks in tendon ducts. And I have seen some very encouraging and very successful applications of that. There are some limitations. So you are able to inspect the first layer of tendon ducts. Anything which is behind there is not visible. Also, partial breaks, so beginning pitting corrosion is very hard to detect. But if there's an actual wire break relatively close to the surface, you will be able to see it. So I have seen a couple of examples where actual proof was done. So the tendon duct was opened and the wires were inspected, and this was up to 100% success ratio. Of course, in actual bridges, sometimes the geometry is so complicated that you can't do the actual measurement because the tendon ducts are too far away from the surface, or they are hidden behind some other metallic object, and then it's difficult. Of course, you need access to the surface. So if the structure is built in a way that you can't do a measurement above the tendon duct, then you are lost. But I'm in favor of this method.
Thank you very much. Alfred?
Yes, so there's also one more question with respect to tomography. In particular, are there recent advances in the phase detection and pulse echo tomography and your experience?
So, yeah, probably this question refers to a little bit more detailed evaluation of GPR tomography or ultrasonic tomography, and not just to provide the location of a certain object, but also of the nature of an object. For example, if we see a reflection from something which is not in the construction plan, we want to know, is it maybe something, is it void, or here some kind of delamination, honeycombing, so something which has less density, or maybe some kind of metallic object which is not just documented in the plans. So, and there are ways to evaluate these, the ultrasonic, also the GPR data actually to do this. So, because depending on whether it's low density or high density, or in case of GPR, low conductivity, high conductivity, we have a change in polarity of the signer. And this can be evaluated. But that's actually an expert method. So there are a couple of things you have to take into account, and some tricks and treats for this kind of analysis. So you need training to do this.
Perhaps I should detail a little bit more this question. The question was going also in the direction of the change in the detection, the phase change in the detection in the tomography. If there are some years ago there were some issue, if there are some new experience, or if this issue is already solved. They are talking about the ultrasound tomography. And
so in phase change, so I think so not that many commercial pieces of software are really offering this option to check for this kind of phase change. So I can just talk here from my personal experience or the experience in my group. There are a couple of applications where it works quite good. So for example, for these crack-like structures of these nuclear repositories. So there it worked very good. We were able to prove these are actually cracks, and it's not just kind of a metallic object which was built in there. And there are a couple of similar things. We had sometimes issues with a very important kind of application, and that's the location of voids in tendon ducts. That's has been a big challenge. So it's of course a very important testing task, because that might be a source for corrosion and other issues there. And it's many people try to locate this. There, the success rate highly depends on the orientation of these voids toward the surface and the accessibility, and so we also sometimes got a bloody nose when trying to do this on site. So we had some cases, especially in the early phase, when we predicted, okay, there shouldn't be a void, and there was one, but also the other way around. So false positives and false negatives both happened. So meanwhile, we are getting a little bit better, but it's still challenging. I think it's not in the state that we probably could write a standard about this. So a simple procedure, and if you follow this procedure, you get a very high success rate. So it's still a method which is only partly commercially so applicable. So I think more research has to be done here.
Thank you very much. So I give over to Professor Radi.
Okay, there was another question which is very practical. What is the practical depth for embedded RFID sensors?
So for my colleagues developing these sensors, they are giving 20 centimeters as a limit, but 20 centimeters would then be the position of the coil which is used for energy supply inside and data transmission on the outside. The sensor itself can be at a different place. If you then have a cable internally from this coil to the sensor can also, and the sensor electronics can be deeper. So if you're using the reinforcement cage or some stirrups or whatever is there available to have a safe place for the cable, so this works as well. So, but still 20 centimeter might be a challenge for this coil if you have dense reinforcement at the surface. So I would say it should be more like this coil, like 10 centimeters. Of course, you can improve this depth in developing better coils or using much bigger coils. But of course, I don't think it's very useful to put very big coils in the concrete because it would weaken the structure. So, but I've seen applications in the nuclear repositories where they used coils of 2 meters diameter, but of course for application of bridges, that doesn't make sense.
Thank you. Alfred, your turn.
Yes, so another question about long-term monitoring. The most feasible technique for long-term monitoring of crack propagation, chloride ingress, and concrete degradation under theta marine exposure. What is the most feasible technique?
There's a simple answer. So there's none. There's no single technique which can cover all these issues alone. I would also always recommend to use a combination of methods. And I would also always recommend start with a thorough analysis of the structure first and the potential degradation scenarios, because that's required to choose the right method and also to put the sensors in the right location. Because in most cases, it doesn't make sense to put sensors everywhere. So that would be also ineffective and too costly. So do whatever kind of analysis is appropriate for the structure first and then select the proper technique. So if you're directly talking about cracking, so for example, to determine the point in time when the cracking happens, acoustic emission would be a good tool. So, and for example, this method is now very successfully applied at a couple of bridges in Germany to detect wire breaks in tendon ducts. For example, at the bridge I've shown in the Genstorbrücke close to Ulm, they have an acoustic emission system. And I think there are a couple of bridges now additionally monitored by acoustic emission each year in Germany. So, but acoustic emission is not, it's also able to give you the approximate location where the wire break happens, but it's of course not able to give any kind of information about the change in structural behavior or structural safety. Then we would need other kind of methods. You would also always need probably some kind of conventional sensors like LVDTs or strain gauges to check whether your numerical models are working correctly, to validate them. So, but at certain points. And then as another addition, so some of maybe this kind of ultrasonic monitoring I've proposed might be very useful in the future, because you can, with a couple of sensors, you can cover a certain important part of the structure and check for changes there, and also give some quantitative values, for example, changes in the elastic modulus or something like that. And it's also sensible for checking for crack development there. So, of course, fiber optics has some very important applications as well. So it's really, as buildings and bridges are unique, also the monitoring solutions in the most cases unique.
Thank you very much.
So, now let's come to this very particular question. Let's talk money. And there are two questions actually which are related, and there's in addition to it. The first one, of course, you can just give us probably the sample. What are the cost of development of NDT methods up to now? Or maybe you can give us a short overview. How long does it take, and until you have really a good method? And finally, if you want to test concrete, what are the sample of the cost per square meter, or maybe linear meter of the concrete? And related to that is also the question, yes, what are the candidates? How do you get a candidate when you want really to apply your NDT methods? You're probably not going to do for every single bridge like 2 meters span. You're probably going to do it for something else. So interesting is this decision, this first decision, what would be the candidate for NDT? So there are related question, because of course there's our economy playing a role there. Please.
Yeah, I probably could give you a simple answer. So I'm the NDT or monitoring guy. So someone else has to decide which bridge to monitor. So so I can give an example about how currently the development is in Germany. So there are about 2,000 bridges which, after the standard bridge inspection, so visual and tap test and maybe some other simple methods, were put, and then some basic analysis was shown to have issues, whatever these issues are in concrete. So, and then there's a stepwise procedure to really do the reassessment using quite simple methods first, and then it's shown, okay, the bridge is still capable of keeping up with the loads, and then for a certain amount of time, so the analysis stop, and then it's going stepwise. If not, so more sophisticated methods are used until in the end a full probabilistic assessment is done using finite elements and whatever kind of means. And if in this process the structural engineers see, okay, there's a missing information, so because the drawings are not reliable, because I've just the design drawings are not as good drawings, so then it's probably decided, okay, let's check this on site by either shaking samples or making NDT. So the decision whether to do NDT or SHM normally is not done by the NDT and SHM guys, it's done by the bridge managers or authorities or whatever kind of thing. So, and if it's done in a proper way, then there is probably first some kind of benefit analysis is done. So, for example, it's you have to think, what kind of information do I need? And when I'm getting it from NDT, is it really improving my situation somehow? So is there a chance to improving the load capacity index or the reliability or whatever parameter you are after? So that's...
And the cost?
The cost is, of course, that's very a complicated thing. So take into account that all these buildings are extremely expensive. So it's €1 billion asset, and probably the most important asset our economy in Europe is the traffic infrastructure. So it's really worth putting some money into it, into rehabilitation, but also into testing and monitoring. So probably for these one-time tests by using ultrasound or GPR. So a good first guess is, so if sending a crew on site doing some measurements and then writing a report later on and do some evaluation will cost you something between 1,000 and 2,500 euros a day. So, and then depending on the site, probably different, maybe a couple of square meters or a couple of or dozens of square meters, and so can be covered. So it's also a hard question to answer.
Okay.
So the other easy answer would be, so the hourly rate of BAM, for example, is 126 euros. That's by law, so it can't be changed there. Probably most engineering firms are cheaper. So for the structural health monitoring installations, the sensors are in most cases not an issue. So they are relatively cheap. So for a bridge, so installations might be between a couple of hundred to a couple of thousand, maybe few 10,000 euros. The devices, for example, for fiber optics or also for acoustic emission, they are expensive. So they have to check, is it worth buying one? It might cost a 6-digit number. Or do I need it just maybe for a year to have maybe 1 year of monitoring and then check whether my behavior is okay or not? So instruments can also be rented, so don't have to cover all the costs by one project. But this has to be taken into account. So monitoring systems, if you buy them completely, you easily go towards 6-digit numbers. And that's just the purchase price. Operation price comes on top of it. But just imagine what it costs to close a bridge and to deviate the traffic. So in comparison, in most cases, monitoring is cheap if it can help to keep a bridge open for a couple of years.
Thank you for that. I would like also to ask audience not to pose any questions. We are over the time already, but we have a couple of questions still to be answered. So please stop asking questions at the moment. And I would like to give back to Alfred with your question, Alfred.
Thank you. So there is also one question going in this direction of the quantification and the extent of non-destructive testing to quantify damages. So I think you answered this in the previous question, but also in the second direction, the participant asked the importance of the quantification and the integration in a BIM system. So what do you think about that?
That's a very important thing. So I have mentioned that in the past, so sometimes NDT was limited to provide these colorful pictures, which are mapping, reinforcement, or tendon ducts and other kind of things. Of course, you can put these pictures into a BIM system because BIM is able to store images and even with the location information. So, but that's then just half the story, because if you would probably like to extract the data from BIM for structural analysis, you don't need these pictures, you need values. That's still a challenge. So in the moment, that's done more or less manually. Also in the cases I've shown, there's still a lot of manual work. So there's still a gap in the software providing so numerical values and also to calculating more or less automatically the uncertainties. So also some BIM systems have issues with coping with uncertainties because all the information which is coming from NDT or SHM has an uncertainty. And so values can be stored easily in BIM and given to some other systems, but uncertainties, that's still a thing which is not easy to be implemented. So that's why, and there's a working group in the German Society for NDT starting to work on this. Probably these interface formats, giving NDT information to BIM and then from there to the other things, they have to be extended or even new formats for this kind of information. And this is to be standardized in a way so that all BIM systems can cope with it. And there's an initiative called Building Smart. It's a European initiative to do this kind of standardization. So, and we have started to talk to them. So, but that's in the moment. It's a wide open field.
Thank you very much. Okay, I can go to Rada.
Okay, thank you. There is another question here regarding impulse response test and regarding best methods to determine residual pre-stressing force in bridge. And regarding your experience, would it be better to determine by vibration test or static test?
That's also a good question. So starting with the end, static test or static load test, I think any kinds of load tests, I think they're not done often enough, because sometimes, of course, not full load tests until destruction. So just service loads to check the reaction of the bridge with whether it's in a way that is expected. That's a very valuable test. That's the actual proof for all other methods. So that's really valuable information. Of course, that's also an expensive test, but in many cases it gives the best information you can get. So for any kind of vibration test, there are a couple of things you can do with that. So including tests like modal analysis or any kind of more sophisticated test looking into eigenfrequencies, eigenmodes, or other kind of analysis. But so far, most of these have limited resolution. So you might see a change if it's strong enough, but in many cases, it's very hard really to find the location and also the amount of damage. So there are a couple of lab tests or numerical tests where this is successfully used, but on actual real bridges with all the variations in material parameters and geometry and so on, it's a quite hard thing to do. So there are a couple of recent research projects. So we have one, but other ones are also working on this, using simply ambient noise and to check the vibration characteristics due to traffic or wind or whatever, at least to see the global changes or regional changes, let's say. So that has good potential, but to go to the details, it's very hard. And to go quantitatively to the pre-stressing force, probably that would be, at the moment, I would be a little bit careful with that. So there are a couple of methods which can at least help to see pre-stress loss. For example, we have done some tests with our ultrasonic monitoring methods, and that was successful. There are also a couple of other ones. Actually, we just last week, we did a test on a real bridge shortly before it was demolished. There were some tendon wires cut intentionally, and several monitoring methods were checked whether they really can detect this and also give quantitative values to this. So probably late summer, autumn, you will see the publications from that one.
Thank you. Alfred?
Yeah, there is one.
I would just like to say that's the second last question, and then, go ahead, from your side and from my side as well.
Good. Yes, there's one interesting question about robotics in non-destructive testing, on combined testing techniques. Is it practical already or not yet?
I would foresee a big potential for robotic testing, especially if it comes to modern building methods. So for example, if you're starting to talk about 3D concrete printing or any kind of prefabricated construction methods. So there's a huge potential to use robotic NDT as a quality assurance method. So for existing infrastructure, so in many cases they have been built in a way so they're unique, so there's no serial production, so all these robots have to be adapted to a lot of kinds of constructions, and so probably that's a much larger challenge. So I think the premier way of using this would be in quality assurance of new constructions, prefabricated ones or printed ones.
There is a question which is not really technical, but rather related to the cooperation of BAM with other research institutes, and it goes like that. How considerate is BAM about data sharing with researchers outside of BAM on their experiments with regard to collaboration and possible improvement of existing technologies? I think you can answer this question quite easily, right?
Yeah. So we do share research data. So at the moment, so that's one way we still have to do. We're working on this. We have some examples on open data. already. So, but just a few ones, I have to admit. We are planning to do more of that, so that all researchers can use a specific data set to test their analysis methods or whatever they want to do with it. So at the moment, we are sharing data with interested parties. So, but that would be a one-on-one discussion on what he or she wants to do with the data, and he will get one. So we are also sharing our objects. It's also possible to come to our labs and share our vast amount of testing specimen and large bridge elements to do some tests there and then to do joint work on the data.
Great. Alfred?
I have two more small questions. The one is with respect to what do you think about the capability of using muon imaging on overlayer systems to detect subsurface defects?
So I'm not sure whether I got the question right.
Muon.
Yeah, what was muon imaging to detect what?
To detect subsurface defects.
I know that there are, so we'll talk about concrete now. So there are also some ideas how to use this in mining or in checking the near surface earth. So that's interesting for a geophysicist like me, but probably not topic of today. So as the amount of muons going through an object depends on density. Of course, it should be possible to check for density changes in concrete as well. So, but there's still a way to go. If you look at the current pictures, there's still a lot of noise and there are some artifacts. So that's nothing which will be market ready next year. So that's probably something which might be market ready 2024 or 2025, other kind of, so in this kind of area. But then, so you could check, for example, a bridge deck. If it's accessible from top and bottom, you could check it for, honeycombing or similar things.
Okay, so that's now the last question from my side, and Alfred has another one. And this is the question which is a bit provocative. It's saying, is NDT-CE, non-destructive test and civil engineering, still a niche market in the whole NDT field? And there are some big players that are missing. There is a company named here, I don't want to mention it here. And is the European community not spending enough, although they have quite a few of old bridges? So what's your opinion on that one?
Compared to the amount of money spent in other industries, you could call it a niche market. So because much more money is spent on NDT, on pipelines, on nuclear power plants, and oil and gas, many other explanations. So the answer would be yes, but I think it's going to change because due to the aging infrastructure worldwide, so there's a higher demand for that kind of thing. Also, due to talks like this or to associations like Eurostruct, but many others, so the knowledge is spread more and more to civil engineers, but also to authorities and other stakeholders. So we're seeing quite a good increase in these markets for service providers, for instrument manufacturers, also for others. But still, we shouldn't blame anyone else. So the NDT community, should also work hard on providing better quality, on providing more talks, more trainings, more information to stakeholders to help to increase the market.
Alfred?
Yeah, one question with respect to the costs. For the testing from academic institutions and private companies, about the differences. Are there differences in general or not?
So you're mentioning, so if I'm hiring a research institute or hiring a company. Yeah, so in Germany, so for our institute, so we are governmental, so it's a bit different to academic. So if engineering firms are able to do the job, we are not allowed to do the job. So there's a simple rule for that, and we are sticking to that rule because that would simply be unfair. And the other thing is that we would have, so our hourly rate is much more than the one of a commercial rate. If it comes to universities, it might be different, but so I don't feel comfortable to give a general judgment. because at the moment often it's the problem is not the competition between academia and firms. Maybe in some cases, in many cases it might be just finding someone who is able to do the job. So, for example, we get a lot of, for example, calls from authorities. Can you do this and that? And then I try. So we can't do it. Can we find someone else can do it? It's sometimes more work available than people able to really to do a good job. So I don't see a very big issue here.
Thank you very much.
So, thank you. Now I would like to wrap up this beautiful afternoon with you, Ernst, and learning quite a lot of things with you together. And I would like, first of all, to thank you for having time and spending us with us today. And then I don't want to miss the opportunity to thank to Sergio Fernandez, who is actually taking care that everything goes smoothly. He's the one that organized everything also with the questions. And so again, many thanks to you, Sergio. And the final word I would like to leave to my co-moderator, Alfred Strauss. And from my side, stay healthy and have a good evening.
So also from my side, thank you very much, Dr. Niederleithinger, for this presentation. It was very impressive, and we learned a lot from your presentation. It was very clear. Also for the audience, thank you very much. Also for Sergio, thank you. And from my side, I wish you a nice remaining week, and all the best, and stay healthy. Thank you very much.
Okay, yeah, thank you also for having me, and it was my pleasure.
Thank you. Bye-bye.
Bye-bye.
Bye-bye.